All right, perfect. Hi, good evening, everyone. Warm welcome to all of you who have joined here for the webinar on battery management system and more focused on BMS algorithm using the model-based design. To deliver this session, so we have Venu here. Venu has studying MSc in vehicle engineering from KTH Sweden, so he's also a part of a battery development team at KTH Formula Student. And Venu is also a co-founder and CTO at Decibels Lab, engaged in all the activities for the electric vehicle segment. So it's a great pleasure to host you on this occasion of this webinar. So what interests us to host this webinar, it is just the pure passion towards EV and to share the knowledge and to sort of mutually learn each other. We've been engaged in the business of EV for over 2 years now, and even more than that. So we've been engaged with a lot of OEs and startups in the areas of consulting. And that's another side of it, but also on the areas of training and services for various even startups and Taiwan suppliers, and also with colleges and academics. So in constructing all of this, Venu has been working on activities of model-based design for BMS algorithms for quite some time. And also with his access to certain labs at KTH, so we were able to conduct very much of the experiments and validate the model, because there is no big deal to sort of build a model, build an algorithm, because you could just go to a MATLAB website and just find a source and download it. It's just straightforward. It's so easy to do that, right? But actually, the meaning is like to find the things behind it and create a logics on our own. And on top of everything, validating those results are a very important thing, because you could build a model, but if you don't know what is its accuracy and repeatability of the results, so there is no point that model is a model basically with respect to industry needs. So with our great chance to access these lab facilities and conduct the real-time testing, the very, very important focus was to sort of validate the model results we have got, and we are able to create the results with the model about 96-97% of accuracies. So it's a great pleasure to have all this experience and exposure working with real-time equipments and industry equipments and cell cyclers and testers, and also being able to get a lot of consulting services from many other experienced people to ensure the models are right. So that's our background of what we have worked with, and on similar, we have created a very mature learning content on various activities, so which we can discuss at the last. So with all of that interest, we're going to bring some insights on what we have worked. So that's what this webinar is all about. And you can be frank enough to ask questions. It's preferably if you could drop a text message in the group. The chat box there, it would be really fantastic, so it doesn't disturb anybody else. So, and as far as the time picks up, so we will take your question and we'll answer you back. And yeah, you never hesitate to drop any questions. No question is a bad question until it's asked. So go ahead for questions, and we would like to have more of an interactive session as much as possible. And over to you, Venu, to take out the session and provide a great learning experience to participants across for the session. Thank you very much, and over to you, Venu.
Yep, thank you. Hello, everyone. Welcome to the session. So I hope you can see my screen and you can hear me. If so, yeah, we'll start ahead the session.
Yes, Venu, it'll be good to go.
Okay, thank you. So yeah, so as Suresh told, like myself, Venu, I have been working on this electric vehicle powertrains simulations and stuff. Now I have been more focusing towards on batteries and battery pack development stuff. From quite some back time onwards, I have started working on cell testing and developing some algorithms for BMS and stuff. So these are some of the ongoing projects for me. One is estimating the state of charge using the Kalman filters, and also developing some models to understand pack level studies or pack level behavior of the battery pack, and also developing algorithms for protection circuits and cell balancing, state of health estimation. So some quite good work is going on, and some quite outcomes are coming out of this testing and stuff. So today, this webinar is mainly focused towards BMS. So what exactly the BMS will do, and what are the functionalities of the BMS, and how to develop the algorithms for protection or for estimating state of charge or for state of health. And also I'll discuss about like a little bit about cell balancing. And in the last, I'll try to focus on like cell dynamic characteristic model. So yeah, with this, I will start ahead with our topic, BMS. So yeah, most of you know about like what exactly is the BMS and what it is, why we are using this BMS in battery packs. So I don't want to go like very basics of BMS. I'll touch base on like mainly on algorithms. And also I don't want to go into like electronic part of the site, because as this webinar is mainly focused towards how we can develop algorithms, or like how we can develop some control strategies to protect the cell from various unfortunate things that might happen in the during the operation. So yeah, basically BMS stands for like battery management system. So the name itself is telling that it is managing the battery pack in order to not go into like some other region where the battery will be having like a bad efficiency, or like will be having like a bad operating characteristics. Okay, so why we have to use this BMS? So the first foremost important thing is like for the safety of the operator. So who is operating the battery pack, or like who are in the vehicle. So this BMS is uh, solely responsible for that, for the safety of the operator. So how it can give the safety to the operator or the people in the vehicle, or to the whole vehicle itself. So these are the things that the BMS has to do in order to protect, or like to give the safety to the operator. So first thing is like it has to detect unsafe operating conditions and respond according to the unsafe operating conditions. So what are the exactly like what are the different types of unsafe operating conditions will be there, which means like when we are discharging the cells drastically, or when we are abusing the cells, or like when we are operating the battery pack in out of temperature zones, or when there is a short circuit happening in the battery pack. So these are like unsafe operating conditions, right? So in those conditions, the BMS has to come into picture, and it has to detect those things, and it has to respond according to those things. And next thing is disconnecting and isolating the battery pack from the load. So if we can do that, then most of the hazardous things can be stopped, right? So if you can't isolate the battery pack, then what will happen is like it will go on spreading in the whole vehicle, because there are like many components in the vehicle, electric vehicle. Uh, I mean like electronic components with that were there. So it will become like a more hazardous thing. So it has to isolate at that point of time. That's like also like major goal of the BMS. And after doing all these things, it has to tell the operator, okay, this is where something is going wrong. So how it can communicate with the operators? So for that, it has to show some kind of display, or by giving some kind of alarms, or like making some noise. So this is like a secondary functionality of the BMS. Okay, so coming to the next aim of the BMS is to protect the cells of the battery pack. So as we discussed, there are like many reasons why the cells will go into like a bad region, or like when we are operating the vehicle in like bad conditions, or like when we are going out of the limits of the cell defined region. So then the BMS has to come into picture, and it has to protect the cells. So how it can protect the cells is like through active intervention under a software control. So there will be like a software. I mean like BMS is like software where it can stop cell discharge and charging, and also like by detecting the failures. So that's what we have discussed in the first step, and isolation of the failed components. Okay, so by these ways it can protect the cells of the battery pack. If it's not protecting the single cell, then what will happen is like it will spread on from cell to cell, and the whole module and the whole battery pack will get like a problem, and it will result in like some fire accidents and all the stuff. And nowadays we are seeing like so many fire accidents because of this lithium ion batteries and stuff. And also to prolong the life of the battery. So what this BMS will do is like it will make sure that the cell is operating in the best operating conditions within the limits. Either it may be like a voltage window, or SOC window, state of charge window, or it also because in temperature window. So it will make sure that the cell is operating in the defined operating regions by the manufacturer, so that the resistance will not develop in the cell, and the life of the battery will increase. So it will take care of that. And it also gives advices in terms of limiting the power. Okay, when we are discharging high power from the battery pack, so there will be a point where we'll reach like a safety margin, and if we cross that safety margin, and if you enter into like a danger zone, then we can't bring back the cell, which means like the cell will become like a irreversible cell. So we should not make that the cell goes into like a irreversible region. Okay. And another thing is like controlling the thermal management system. So nowadays, like the thermal management system of the batteries plays a very, very important role, because most of the issues related to battery pack or because of this thermal. So how we can develop like cooling channels, or like how we can develop how we can place the cells in the battery pack or in the module, so that we can have like a proper cooling to the cells, each and every cell, like that. So yeah, it will control the thermal management system, and the main goal is like operating the battery pack in proper range. Apart from all these things, it is also the other important thing is like maintaining the battery pack in a state which it can fulfill its functional design requirements. Okay, because many people will be telling that we should not operate the battery pack in between like 100 to 90 percentage, or from 10 to 0 percentage. So what this BMS has to do is like if you give some command to the BMS telling that my battery pack has to operate only in between 90 to 90 to 10 percentage, so then it has to make sure that the battery pack is operating in this region. So what will happen if it goes between 100 to 90 and 10 to 0 percentage? So nothing will happen to the battery pack, but the health or like life of the battery pack will be decreased, because in this region we'll be having like a more of polarization developed in the cell, which means like more resistance will be developed in the cell. So that's the reason we have to make sure that the battery pack is operated in the defined SOC window or SOC window, and limiting over discharge and overcharge scenarios. So when we over discharge the cell, we all know that like the losses that happens in the cell is in terms of like I square R losses. So when we over discharge or like overcharge, this is the term which is getting like multiplied I square. So instead of 10 amps, if you are discharging like 100 amps, so then this will be like a 10 power 4 times R value, which means like the power loss happening in the cell will be like almost very big. So that's the reason like we have to limit during the discharge and charge. So this also depends upon like the cell selection, like not only the property of the BMS, we also have to select like a proper cell when we are making the battery pack. Okay, so yeah, these are like main important things why we are using the BMS. Apart from this, we are also having some functionalities that this BMS will be doing. So basically I have divided these functionalities into like two types. One is like primary functionalities, and the another one is like secondary functionalities. Okay, so coming to the primary functionalities, there are like four important things that the BMS has to do. One is like sensing and high voltage control. So whenever we are going to develop some algorithm or like protection logics, we need some data. So what exactly is the data is like we must know like cell voltages, cell currents, and cell temperatures. These are the three important data that we need to develop like algorithms and protection circuits. So this functionality of the BMS will sense the data like cell voltage, cell temperature, and cell current from each and every cell of the battery pack. Okay, and it depends upon like how we are connecting the cells and modules. Okay, and also like it depends on how much data you want. Either you want only the series data, because voltage will only be in series, not in parallel. So some people will be doing like collecting the data only of series cells, not the parallel cells. Okay, so it solely depends upon you how you want accurate estimation of the algorithms. So yeah, this particular functionality will measure the cell voltages, cell temperatures, and cell currents, and it also detect isolation faults, isolation with respect to the chassis or with respect to like other electronic components and other mechanical components and stuff, and controlling the contactors. Okay, so these are the five important sub functionalities of the BMS. And the second thing is like protection. So in protection, the BMS has to make sure that the cell is operating between under voltage and over voltage limit. Okay, if you take like a lithium ion cell, and if you look into the data sheet of lithium ion cell, there will be some kind of limits for the particular cell in terms of voltage. One is like over voltage, under voltage, and the nominal voltage, and the third one is like nominal voltage. So this nominal voltage will be using mainly for determining the battery pack size, so that will be on the safe side uh, when we are in the limits of like under voltage limits, are like when we are reaching like over discharge. So in order to be on safe side, we'll go with like nominal voltage when deciding on the battery pack size. But when we are discharging or charging the cell, we'll try to make sure that the cell is operating between these two limits, over voltage limit and the under voltage limit. So basically for lithium ion, it will be most probably 4.2, and this will be somewhere around like 2.8 volts. This might vary with the zero point 0.1 or zero point 0.2 tolerance values. But yeah, these are the limits for like most of the lithium ion cells. That's the one important priority of the protection circuitry. And next one is like controlling the current that you are discharging and charging. So if you look into the data sheets again, there will be like a C rates, which will be defining you like how much current that you can discharge from the cell. So let's say like if your cell capacity is like 10 amp hour, then they'll mention like continuous C rates as well as like peak C rates. So if they say like continuous is 10C and peak is like 15C, and for this peak they'll mention the time also, which is like 5 milliseconds or like 10 milliseconds, which means that 15 times of 1C, so it will be like 150 amps. We can discharge only for 5 milliseconds. If you cross this limit, what will happen is like the power losses will increase, and the temperature will increase. And if the temperature increases, the chemical kinetics and the reaction electrode kinetics will start increasing, and it will go out of the region, out of the control. Okay, so that's the reason we have to control the current that we are discharging or charging. So that will be in terms of like C rates. Okay, so as I told you before, it's not only solely property of BMS. So it depends upon our selection also, the cell selection. If you have selected wrong cell, and if you're using it for like other application, then the BMS can't do anything. It will just simply shut down your battery pack, and you'll not get like achieved performance or like a targeted performance from the vehicle. And the third protection is like temperature protection. So basically lithium ion cells, yeah, similar to like voltage, it also will be having like a temperature range. So if you look at like charging, it will be like a 0 to 40 degrees Celsius or 0 to 60 degrees Celsius. But when you look at like a discharge, it will be like ranging from -20 to 60 degrees Celsius. Okay. So we have to make sure that when we are charging the battery pack, this is the temperature that is maintained in the, at least in the vehicle or in the battery pack surroundings. Okay, so how we can let's take an example of Sweden. So here the temperature will be always like 1 degree Celsius or something like that. So how we can bring that temperature? So at that point of time, this sensing functionality will sense the temperature of the cell, and if the temperature is like almost less like 1 or 2 degrees Celsius, then it will send the signal to the vehicle control unit saying that the temperature is very less and we need like some kind of temperature over there. Then the heater might be switched on, and it will try to bring the battery pack to like certain temperature range. Okay, so these are the three important production functionalities. And the other two important things is like cell short circuits and external temperatures. Okay, so these are like secondary of protection. So external temperatures is like solely depends upon like environment conditions. So we are not going to discuss regarding that, but when I'm explaining the algorithms, I'll try to explain these 3 points, which are like cell voltages, cell temperature, and cell currents. And these three things: voltage, current, and temperature protections. Okay, and the third one is like estimation functionality of the BMS. So here we have to estimate SOC and SOE, so state of charge, because state of charge is very very important in the cell, because every parameter of the cell, lithium ion cell, either it might be internal resistance or it might be terminal voltage or open circuit voltage or like the dynamic resistance, each and everything is a function of state of charge and temperature. So if you're not estimating proper state of charge, then we are uh, we are not properly estimating other things also, right? So that's the reason like we have to estimate accurate SOC. And also like this SOC plays very important role in cell balancing, because there are two strategies that we'll be using for balancing the cells. So one is like a voltage based strategy, and another one is like SOC based strategy. So there it will play a very important role. If you're not accurately estimating the SOC, then your cell balance will not happen that properly. And state of energy. So this state of energy plays a very important role in like estimating how much amount of capacity has been utilized for each and every cycle. So and it also helps in like estimating the state of health, and like how many like cycles we can run more, something like that. And this SOC, I forgot to tell, this SOC also helps you in like range estimation. So let's say like we'll be looking at our dashboard and we can see like how much percentage of capacity is left out. So if it is like 50 percentage, we'll get to know idea, okay, still 50% is left out, we can travel this much of distance and something like that. That's where this state of charge plays a very very important role. And the fourth important primary functionality is balancing. So here balancing comes like most probably cell balancing, module and pack level balancings, and also like multi-pack levels were there. Okay. So we'll be, there might be some bad cell which goes into the module. We don't know like why it went wrong. It might be because of weak electrolytes or weak electrodes present in the cell. So sometimes it might go wrong. Because of that, what will happen is like the BMS will always shut down the discharge and charge circuitry, because this weak cell will tries to attain the defined state of charge or like depth of discharge within less period of time. Okay, so that's where like the BMS will think that okay, this cell has already reached the SOC, and it will try to switch off the whole battery pack. So that's the reason like we have to always try to balance the cells, then in order to get like best performance from the battery pack. Okay, so yeah, these are like primary functionalities of the BMS. Now looking at like secondary functionalities. So the one is like interface and the diagnostics. So interface means like there has to be some communication between like the BMS, battery pack, and the vehicle, and to the person who is operating all those things. If there is no communication between these things, then we couldn't find out like where there is a problem or where there is a detect happening. So we can't do anything. So we need to have like a proper communication between all these things. So this interface should report all like cell defaults, or like the problems in the cell module level and also like pack level. And it also has to show like a status of the pack in terms of SOC, state of health, and state of energy. So present day BMS at present, most of the BMS were like representing the state of charge but not state of health. So still some kind of research work is going on like how we can implement SOH into the BMS. Okay. And yeah, finally it has to also show like errors, abuse events, and all the things. Coming to the diagnostics, one is like state of health and state of life. So these are the two important parameters. Both like finally these two terms refer the same thing, which is like health of the battery pack. So what nowadays what people are doing is like or the industries, what they're doing is they are collecting the cells from the used vehicle at different SOH levels. So let's say like 90 percentage to like 10 percentage with a step of like 10. So at 90 percentage, how the cell is behaving, which means like when state of health is 90 percentage, it is not state of charge. So state of charge is like we can continuously regain this state of charge. Let's say like if you discharge the cell from 100% to 0 percentage, and again we can achieve this 100% state of charge. But whereas in state of health, once we reach like a 90 percentage, it always it will be in like a decreasing mode. We can't increase this state of health. Okay, so that's where like when state of health is 90 percentage, how the cell is behaving or like how the electrodes are behaving. So based on that, they are trying to collect the data and trying to develop some models called as like a neural network models or like data driven models. And they are trying to implement these data driven models into like a BMS. So what will happen is like as the time goes on, as we are using the vehicle and the battery pack, our SOH will be decreasing, and we can uh, based on SOH, we can predict like how the range of the vehicle will be going to be affected, or like how the SOC properties will be going to be affected. Okay, but yeah, this is still in like research is going on this part. But now what they're doing is, instead of this full model, they're just implementing SOH using like Kalman filters, like extended Kalman filters or like concentrated Kalman filters. They're just predicting the values and they're implementing that programming into the BMS. Okay, so these are like the main functionalities of the BMS. I hope you understand like what are the different types of functionalities. So now what I will do is like I'll try to discuss at least like one from each of these functionalities. So in sensing, I'll try to discuss cell voltage, cell temperature, and cell current, how we are going to measure those things. And in the protection also, we are going to discuss like voltage, current, and temperature, and state of charge estimation. So these are the three important things that we are going to learn in this webinar. So coming to the sensing functionality, so the cell voltage. So where we are going to use this cell voltage. Okay, so there are different ways of estimating the SOC, state of charge. So in we can use like voltage lookup based methodology, or Coulomb counting based methodology. I'll come to these things, but I'm just writing over here Coulomb counting based methodology and Kalman filter based methodology. Okay, so in voltage lookup based methodology, we need like a lookup table between voltage and state of charge. So if you are not estimating, or like if you're not measuring proper voltage, then estimation of SOC will be not that accurate. Okay, so we have to accurately estimate this voltage. And coming to the Kalman filters, we'll be using the voltage, measured voltage. So there also, if you are not accurately estimate or like measuring the voltage, then your estimation of SOC will be wrong. Okay, that's one thing. And in the cell balancing, as I told you before, we are having two ways of doing the balancing. One is voltage based and SOC based. So if you're not measuring proper voltage, then the cell balancing also will be affected. Okay, so that's the reason we have to properly measure the cell voltages. So how we can measure this cell voltages? Basically, we will be using like IC chipsets. Okay, so those can be used for like measuring the cell voltages, and these ICs can measure like cell voltage of like a number of cells, maybe 12 cells or like 14 cells, depending upon the IC you have selected. So if you look at over here, this is the one which we have used over here, LTC 680. Okay, so this will be having like this is having the capacity of measuring like around 12 cells, which means like a voltage of 12 cells. If you look at over here, we'll be having like almost 24 probes. So two of these probes will be connected to one cell, and these two probes will be connected to another cell. So like that, we can connect these chips in series, and we can connect like we can measure like cell voltage of modules also. Okay, so the same can be inferred from this image also. So this is like IC, and these are like the probes, and this is like a single cell, and this is another cell like this. Okay, so if you feel like there is a problem, and if you think like the sensing of voltage is not that accurate of using the one single IC, so what you can do is like you can place two of ICs in parallel for fault tolerant design cells. I mean like to reduce this or like to understand like how the difference in voltage is coming. Okay, so basically this is how we can measure the cell voltages. After measuring the cell voltages, we can implement this in like algorithms and protection logics and stuff. Okay, and the second one is like cell temperature. And one more thing I forgot to here, like basically after measuring the or sensing the voltage, we'll be using like analog to digital converters. So for that, voltage is always the input, right? So if you give the voltage signal, then it will be converting it to like whatever the digital signal you want. So you'll be using like analog to digital converters. So the second functionality, which is like cell temperature. So again, we should know like what is the importance of measuring the temperature. Okay, so this temperature plays a very important role in like one is like temperature protection. When we are developing an algorithm for protection circuit of temperature, then uh, measuring the temperature plays a very important role. And one more thing is like we have to develop some cell models. for SOC estimation or for SOH estimation or for like cell balancing, we need some cell dynamic models, which means like how the cell is behaving with respect to different conditions. Okay, we can estimate these things by doing the testing, but testing is like always like depends upon like cost also, right? So always we can't do the testing in real time. So for that, what we'll do is like initially we'll do the test, we'll get some data, and we'll try to implement the data in developing some models. Okay, so in order not to go into testing again, so there this test temperature plays a very important role in developing like those kind of models. Okay, so basically we'll be using like thermocouples or like thermistors. So I hope you might be knowing like the working principle of these thermistors and thermocouples. Okay, basically we'll be having like two types. One is like NTC and PTC. So NTC is like negative temperature coefficient, which means the resistance is inversely proportional to the temperature. If the temperature increases, the resistance value decreases. And for the PTC, it is vice versa. If the temperature increases, the resistance also will increase. So basically, the thermistor, like the working principle will be something like this. So this is the R1 and this is the thermistor, which we'll be using for like measuring the temperature. Okay, so basically this R1 is like independent of temperature. So what happens if you use this also as like a dependent of temperature? So if this is dependent of temperature, this R1 will be varying continuously with respect to temperature, and because of this the voltage drop will be continuously varying. So we can't measure like accurate voltage. That's the reason the one resistor we are taking will be like independent of temperature. And thermistor, of course, it has to be like function of temperature. Okay, so whenever we are measuring something, first we have to think like how we can get the voltage across that particular thing, because if we can get the voltage signal, then we can convert into like as I told, like we can use ADC converters and we can get whatever the signal we want. Okay, so for that we have to do like a little bit of calculations. Okay, you can see these calculations over here. So you can see R1 and R thermistor in like series, so they are like very basic calculations. So if you want to calculate the current across this resistance, it is nothing but voltage across these two terminals. This is like ground and this is like a positive terminal. So voltage divided by the total resistance as they're in series. Then what I'm doing is like I want to find the voltage across this thermistor, because I want to find out this R thermistor, and it is a independent variable, dependent variable of temperature. So it will be continuously varying. So this voltage also will be continuously varying. So that's the reason first I'll find like voltage across the thermistor. So this is the simple formula. And once after getting this, if you rewrite this equation, we'll get like R thermistor value. Okay, the resistance across the thermistor. If you know this thermistor, will be having like lookup tables for that particular selected thermistor. It will be like in between temperature and the resistance values. Okay, and they also will give you like a equation that represents the behavior of that particular thermistor. So here is an example of that equation. So resistance across the thermistor equal to R naught exponential times of beta. Beta is a device constant for that particular thermistor, and it is like 1 by 273.15 plus T, and minus of 1 by 273.15 plus T naught. So here R naught and T naught are like initial resistance and initial temperature values when you're starting your measurements or something, and T is the value that we are looking for. Okay, so we'll find out like R thermistor value and we'll keep it over here. And initially we know like initial temperature, let's say like room temperature. So we'll substitute over here and this R naught value, and we'll try to get this unknown variable temperature T. Okay, so this is how this BMS will be measuring the temperature of the each and every cell. Okay, and we'll be using this temperature in other algorithms. And the third one is like the cell current. So how we can measure this cell current? Before that, why we have to measure this cell current? Where we are using this cell current? Okay, so first important thing is like when we are doing the testing of the cells. So what we'll do is like we'll give some current profile to the test cell, and we'll try to understand like how the voltage is behaving, right? So we can replace the testing with a lithium ion characteristic model. So in that characteristic model, if you want to give like the cell current, I mean like the cell discharge or charge current, then we should have like proper measured data. So that's where like this cell current, measuring the cell current plays a very important role. And another thing is like SOC estimation and SOH estimation. So in SOC capacity, which means like SOC is nothing but like the amount of charge that is present in the cell. So charge is nothing but Q equal to I into T. Okay, so if this current is varying with respect to time, and if you multiply that with time, we'll get like capacity. So that's why like if you have like proper measuring of current, then proper estimation of charge will be done. Otherwise, your SOC will not be that accurate. Okay, so that's the reason we have to measure like proper cell currents and stuff. And SOH also is depends upon like capacity of the cell, how much capacity fade is happening in the cell. Okay, so I'll discuss the term capacity, what exactly it mean in when we're discussing regarding the state of health. Okay, for each and every cycle, let's say our capacity of the cell is like 10 amp hour. After one cycle means like one discharge and one charge. Okay, so let's say like for one cycle there might be loss of like very less amount of capacity. Let's say like it becomes like 9.9999% 99 amp hour. Okay, so there will be little amount of capacity loss. So after like 1000 cycles, so this capacity might come to like 8 amp hour. Okay, so this capacity measurement depends upon like current again, because it is a function of current into time, right? So if you can accurately measure the cell current, then we can accurately estimate the capacity, and then this leads to accurate estimation of state of health. And if you can accurately estimate state of health, it will benefit you in range estimation and battery pack characteristics and all the stuff, and also like internal resistance development, these properties. Okay, so how we can measure this cell current? So again, here we're having like two methodologies. One is like current shunts and Hall effect sensors. Okay, so here you can look at like the one example of using the current shunt. So this is like a positive terminal of the battery pack, and this is like a negative terminal of the battery pack. In the negative terminal, I am connecting a resistor. Okay, so the shunt resistor should have like a very low resistance value. Okay, what will happen if you have like a high resistance value? So we already discussed that point, that is nothing but I square R. So as it is a battery pack terminals, I mean like major terminals, there will be like a large amount of currents that will be coming out of this cell, these terminals, maybe like 100 amps or 200 amps, 300 amps sometimes. If you take it for like race car applications, it will be like 300 amps, 400 amps also. So that's why like it will become like square times of that current, and this power loss will be very high. Okay, so our main aim is to measure the current that is flowing across the terminals. Okay, because of adding this, we are adding more losses. So that's the reason we have to select a resistor that is having very less amount of resistance, maybe approximate around like 0.1 milliohm. Okay, so we can measure the voltage drop across this, and we know the resistance value of this particular resistor. And this resistor we are using, it should be independent of temperature. Okay, if it is dependent of temperature, what will happen is like this always changing. So that's the reason we should not use it as like dependent of temperature. So we can measure like a voltage drop happening across this resistor, and we know voltage drop and the resistance value, so we can find out the current that is flowing through the resistor. So that's the one way, and we can amplify those data that we have measured to the BMS. Okay, this is how it looks, and this is like the shunt. So the second example is like using the Hall effect sensors. We all know like how these Hall effect sensors will work. It basically principle of like electromagnetic field. So when there is a current carrying a coil, and if there is like a coil surrounding that, then there is a chance of electromagnetic field generation. So because of this, there will be like currents that will be generated in the secondary coil that has been uh, kept or the primary current carrying conductor. So this will be like a primary, which is nothing but our battery terminals, and this is the secondary coil which is kept around this primary. So because of this, there will be some electromagnetic field that will be generated, and because of that, let's say this one is I1 and this will be like I2. Okay, using the number of turns principle and using the electromagnetic principle, we can calculate like what is the current that is generated in this secondary coil, right? So after calculating this I2, we can estimate like how much current is passing through this I1. Okay, it's just like very simple formulas. So then we'll be sending this to BMS. Okay, so this is how exactly this Hall effect sensors will look like. So here we can see the halo uh, space where this conductor, primary conductor will be passing inside, and this is like we'll be connecting this to like a electronic board, or like where we can measure the data sensors to this. It will measure the data and it will send it to the BMS. So this is like how we'll be measuring the cell currents. Okay, so now we got like how we'll be measuring the cell voltage, cell current, and cell temperatures. So now we are having the data. Okay, so what we have to do with this data? We have to develop some kind of protection functionalities, or like whatever it might be, some algorithms for estimating the things, or for protecting the cell. Okay, there are many things that we can do with these things. Okay, so first we'll start with like protection. So yeah, in protection, what exactly the protection functionality of the BMS has to do? Okay, so it must be responsible for these six things. One is like undesirable events or conditions. It has to save the cell from that. Excessive current during charging and discharging, short circuits, over voltage and under voltage, high ambient temperature or overheating, and loss of isolation and abuse. Okay, it has to make sure that it has to give protection in all these six cases, or like if anything which I missed over here. Okay, so how we can develop these protection logics? Okay, I'll try to show you an example how we can develop some algorithms or like protection logics. Okay, so now I have some data which I have measured from the using the sensing functionalities before. So using that, I'm going to develop some logics over here, production logics. So first one is like I'm taking current and temperature are the input variables, because I measured the current and temperature. Sorry guys, give me 1 second. Yeah, so now we can start. So yeah, here we are having like temperature on one axis and current on another axis. These are like measured values. Okay, so here we can see like two regions. One is like highlighted in the red color, and the other one is like in the green color. So the green one is like a safe operating zone where we can operate the cell without any issues. Okay, but this is like the red zone is like a failure zone. So this is the limit we can go up to, which are defined by like the cell manufacturer. Okay, but when we are developing some protection logics, what we have to do is like we should not go directly with this defined value from the manufacturer. We have to restrict ourselves to a some safety margin. Okay, so that's where we'll be keeping some safety margin over here. Okay, so and which means like we can move up to here, but this will happen only when this protection and this protection fails. Okay, so here I am giving like 2 degrees of protection. One is like thermal protection and another one is like current protection. So if you look at over here, this is the thermal fuse. So if the temperature increases in the cell, then this if it crosses the limits, then this might failure. Okay, but still this electronic protection will be there. So which means like out of two, one is failed and second one is there. Okay, so if you are still abusing the cell, then this might also fail. Then we also lose like the second degree of freedom also. In that case only this resettable fuse is there, right? Then it will start moving in this direction. Okay, and it will reach like a failure zone. So until and unless, then it will be in this safe operating zone. Okay, we can give like more number of protections also, like 3 degree of protections and all the stuff. But yeah, this is just for an example. I kept it over here. One is temperature and another one is current. But the model which I'm going to show you, it will be like a 3 degree of protection, which is like a current, voltage, and temperature. If any of these thing goes wrong, then the BMS will switch off the discharge and charge conditions. Okay. So if you look at it, this is a second example. One is the temperature, measured temperature, and the measured voltage. Okay, so the thermal fuse remains the same, and the red zone represents like the limitations of the manufacturer, and the green is like our safety operating zone designed by ourselves, but after like keeping the safety margin. Okay, in the voltage we'll be having two things here, because in current only one thing, like either discharge or charge, but here when we are charging and when we are discharging. Okay, so we are having like a over voltage protection and under voltage protection, and also like charger side protection and load side protection. Okay, so here we can see this is 1 degree of freedom, and if you consider these two as like 1 degree of freedom, then it will be one, and here one, so total 3 degrees of freedom. Okay, so this is like a battery. So here we'll define like a over voltage limit of 4.2 volts. So whenever it crosses the 4.2, then the BMS will take necessary actions. Okay, so if you cross this limit also, this charging protection will be there, which means like on the charger side. Okay, and similarly here on the under voltage side, so this will be like 2.8 volts, which is like under voltage limit. So if you cross this limit, on the load side we'll be having the protection. Okay, so this is how we can develop some kind of algorithms. So if you want to develop like a VAT protection logic, so what you have to do is like you have to measure the data, and first before going to develop the algorithms, try to analyze the things. Okay, what are the limits that are defined by the manufacturer, and what you can do in order to increase the life of the battery or like life of the cell. Okay, so try to bring this kind of analyzation into your algorithms, and then go for developing the things. Okay, so now what I have done is like after developing these things, I went for like developing some kind of algorithm over here. So yeah, you can see here voltage, current, temperature, protection functionality, right? So now what I have done is like I have measured the terminal voltage, I have measured like the charge current, and I have measured like the temperature. Okay, this is like a charge VAT protection circuit. Similarly, there will be for like discharge also. Okay, I'll try to show the model also after this, but yeah. So now after measuring the terminal voltage, I'll send it to a comparator. Okay, so what it will do is like if the measured voltage is greater than or equal to 4.2, so it will send either 1 or 0. So 1 means true case. True case means like we are going out of the region, means going above 4.2. 0 means false, means we are in the safe zone, right? We are not going above that. So here we are getting 1 comma 0. And similarly, if you look at charge current, so here I given limit as 60 amps. So it depends upon the cell that you have used in the battery pack. So whenever the charge current goes above 60 amps, it has to send me the output either 1 or 0. So if it is sending output as 1, which means true case, true means we are in the unsafe zone, and 0 means like we are in the safe zone. Okay, and similarly over here, the temperature. So for temperature, there will be like a different scenario, because for charge, there is a limit 0 to 45. And for a discharge, it is like minus 20 to 60 degrees Celsius. So that's the reason we have to make sure that it is operating in between these two values. So for that, what I will do is like I'll use two comparators over here. Whenever the charge temperature is greater than 45, it will give either 1 or 0. And similarly, whenever it is going below 0, so if you look at over here, it is less than or equal to, it will give either 1 or 0. Okay, so in both the cases, it has to the BMS has to take some action. So for that, we have to use a proper logic block. So here I am using like a R block. So what is the function of this R block is, whatever the inputs you are giving to the R block, if any of the input is true, then the output will be true. If all the inputs given to the R block is false, then the output will be false, which means here we are having two inputs. So this is the situation. It will be like this: true, 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 false, false, true, and false, false. Okay, so in this first situation it will send true, in the second situation it will send true, third situation it is true, and in the fourth situation only it will send the false. Okay, which means in all these three cases we are in the unsafe zone, which means the BMS has to come into action, and in this zone only we are in the safe zone. Okay, so but the final output here will be again either 1 or 0. Okay, so now this is like 1 degree of here we are having 2 degree of protection. that has been converted to again 1 degree, and here we are having 1 degree of protection, and here we are having 1 degree of protection. So now for the whole battery pack, we have to define like 3 degree of protection. So that's where like three inputs were given to like this OR logic. So again, the same principle apply here. So it will be like true, true, true like this. So we can develop like a logic sequence over here. So whenever any of the input given to this OR input OR gate is like true, then the output will be like true. Output will be true, or it is, if all the inputs are given are false, then it will be false. Okay. So if it is true over here, which means like we are unsafe. Okay. Unsafe means whenever we are getting some output as 1, we are unsafe. When we are getting output as 0, we are in the safe zone. Okay. So in this unsafe zone, we have to do something. Okay. What we have to do? We have to control some parameter. Okay. So if you look at the temperature and voltage, they're all dependent on current, right? So if you are discharging more amount of current, I square R losses will be there. Because of I square R losses, heat generation will take place. So because of that, the temperature will increase. And because of the current discharge, this voltage depends, like how the voltage is behaving, right? So the only parameter that we can modify is the current. Okay. So whenever we are entering into the unsafe zone, we'll try to control the current parameter, means by decreasing the current to certain amount, or totally switching off the discharge circuitry or charge circuitry. So it depends upon how we are controlling the current. Okay. So that's how we'll be developing the logic and algorithm. So this I have developed in the Simulink. So similarly, you can develop in like C coding or whatever the platform you want to use. But Simulink is like one of the platform where we can visualize the things. Okay. So now what I have done is like I have given all these inputs to the dashboard. If you look at over here, this is the discharge dashboard, and this is like a charge dashboard display. So whenever we are going into the unsafe zone, these LEDs will blink like red in color. Whenever we are in the safe zone, it will show green color. Okay. So that the operator will get to know that, okay, uh, because of voltage we are facing some problems, or because of current we are facing some problems, or because of temperature we are facing problems. So which means like we are meeting our interface our communication functionality also. Okay. So this is about like voltage, current, and temperature algorithm. So if you look at over here, this is the full model of that particular thing. Okay. So here, the one I showed in the previous slide is will be inside this particular block, discharge BMS and charge BMS. Okay, we can implement everything in a single BMS. Okay, but why I have divided into two things is like to make myself validate whether the things were going correct in the discharge and charge BMS, and to understand properly whether everything is going good or not. Okay, so this is the current profile which I have measured, or like the sensing functionality of the BMS will measure the current. And here we can divide this current into like a discharge current and charge current, and we'll send this to BMS, and here also we'll send to the BMS. So first protection that will be applied over here is over current and under current protection. So whatever the current over here, it will go through the protection logics, and if it is okay, then it will come out as like a feed discharge current. Then this will be sent as input to the, I mean like sent as input to that cell, means the cell is allowed to discharge. Okay. So here I'm sending that as input. So the cell is now given the permission to discharge. So it will discharge, and the terminal voltage, we can calculate the terminal voltage and the temperature. And again, now what we'll do is like in the time t equal to at time t equal to 2, we'll give all the three as inputs: current, temperature, and voltage. So now all the three protection circuits will start working. So okay, so based on that, the current will get modified, and this current will be sent to this. So like this, everything will be working in a loop. Okay. So I hope you got a little understanding of this model. So now I'll try to show you this model in the Simulink, so that you'll get like a more idea. So give me a second over here. I hope you can see my MATLAB screen. If yes, can you please write us in the chat box?
Yes, we know it's visible.
Okay. So yeah, this is a little bit of coding that I have written for developing the algorithm. So I'll just run this code, and here I've given like so many current profiles, like drive cycles, NADC drive cycle, or like some dynamic profiles and formula current profiles. Yeah, there are so many current profiles that we can test for before implementing it in the BMS. So yeah, so now it is asking me for some input, which is nothing but which current profile I want to give. So I'll give like NADC current profile. So try to understand over here, see over here. Sometime at some point of time it will blink red. Yeah, you have seen, right? Which means like at that point of time, uh, we are in the unsafe zone. Okay, so these are all like tested data, which are a function of state of charge and temperature. We need so much of data to develop like a BMS. Okay, so now if you go inside this, so this is the model which I've shown in the presentation, discharge BMS and charge BMS. And from this, we'll be getting like a feed discharge current as output that is given as input to the cell. And in the cell, we have developed some lithium ion characteristic model or dynamic model that is also again developed using the tested data. If you have this model, then you can analyze your cell behavior for different types of current profiles. And you can also do like constant current discharge test or like HPPC test and yeah, dynamic profile test, impedance test, and all the stuff. Okay. So yeah, I'll just go inside this. So actually this is the logic we have seen over here, but this is for like a discharge. The one which I've shown is like a charge. So in the discharge case, we'll be having like under voltage limit of 2.8. So whenever it goes less than or equal to, it will send either 1 or 0. And discharge current I kept as 100. So it will send either 1 or 0. And the temperature here I mentioned in Kelvin. Okay. So total will get like the discharge either 1 or 0 over here. So as I told you, if it is coming as 1, then we have to do something with the current profile. So what I'm doing with that current profile is, so if you look at over here, I'm using a small, I mean like in Simulink, we can use any kind of controllers. I'm using simple true or false controller. So here, whenever it is coming 1, okay, which means like unsafe zone. So in that unsafe zone, I'm giving 0 as the output current. Okay, which means totally I'm reducing the discharge or charge current. Okay, but instead of that, we can develop some logic. Okay, so to what extent we can reduce the current. Okay, so those things also we can develop and we can implement, but for simple thing, I just kept it as 0. And whenever it is coming 0, which means we are in the safe zone, so the same amount of current has to be given as input to the cell model. So if you look at over here, the same amount of current will send as output over here, and this feed discharge current will be sent to the model, cell model. So that's the basic logic. And inside the cell model, I'll show you like at the end of this webinar, because I'll discuss about lithium ion dynamic model. Okay, so at that point of time, it will give like a more understanding of this particular part. Okay, but this is basically lithium ion dynamic model. So now I'll try to show you some results. So here also I converted like charge results and discharge results. So this is the charge current that the NADC current profile is giving. So if you look at over here, we are reaching like minus 60. Okay, so but now what I'm going to do is like I'm going to restrict this current at like minus 20 amps itself. Okay, so I don't want to discharge more than that. So I'll go to the charge BMS. So in the charge BMS, if you look at over here, I given minus 60. Instead of that, I'll give minus 20. Okay. Okay, so again I'll run it. So you can see somewhere here a red blinks in the red overcharge currents, and it showed right over discharge current. If you run the simulation in a slow pace, then we can clearly see the visualization of those things. But yeah, so now I'll go over here. I'll look at the current profile of the charge. You can look at over here. So minus 20. It's not crossing minus 20. And if you might have observed like a voltage profile also, it has been totally changed compared to the last time. Okay, and the temperature profile also will change. Okay, because we are restricting the current discharge and SOC open circuit voltage, everything R0, R1, C1, state of energy, every parameter will change because of that restriction we have given. Okay, but in order to understand where we are going into like a wrong zone or where we are in the safe zone, there has to be a trigger. So here we are having charge trigger. I'll show that data over here. So this is the charge trigger, and yeah, the same point. Whenever we are going to one, it means like unsafe zone. So if you look at over here, we are going into the unsafe zone. Here, unsafe zone. So these are the zones where we are entering into the unsafe region. Okay, and from this we can also measure the duration of the time, or like the duration in which the cell is operating in the unsafe zone. Okay, so based on that, you can develop some control logic. And this is like for the discharge trigger, so it is continuously maintaining one here for some period of time. After that, it is continuously maintaining one. Okay, so this is one thing. And if you want to do it in the discharge BMS, yeah, we can do in that also. So what I will do is, like, instead of keeping it as 100, I'll keep it as, like, before going over here, I'll show first the results of discharge. So if you look at over here, it is reaching like almost 80. So now I'll restrict to like 40. Okay, so let's see what will happen. So I'll run it. Yeah, it faced the problem of under voltage, it faced the problem of over discharge and these things. So now if you go back to this discharge results, so yeah, you can see here exactly it is cutting down at like 40 amps. Okay, whenever it's reaching like 40, it is suddenly dropping to 0, and again it is increasing. Okay, so that's what happened. But in order to clearly understand, the best way is to look at like a discharge trigger. So I'll show that also. So this is the blue one, is like a discharge trigger. And in the previous part, when we are discharging like 100 amps, we are not having like these continuous ones. Only at the last we are having. But now you can see like we can see some peaks reaching 1. Okay, so similarly you can control the temperature also. We can change the temperature, and you can control the model. Okay, so yeah, and we can give like whatever the current profile you want to give using this particular thing, input parameters. And also you can give initial temperature also, whatever you want, and you can test your BMS. So yeah, this is like a model for protection functionality. I hope you understand. So next, before going into like the estimation functionality, we'll take like a small break for like 5 minutes, and then we'll start. Thank you.
All right, so I think we can catch back in 5 minutes. Cool. I think we have another half the slides left away. Great. All right, so take a break for 5 minutes.
Well, we can try to answer some of the questions over here.
Yeah, don't worry about it. I'll take care of it. No issues. Take a break, and we'll be back in another 5 minutes.
Okay.
Cool. Okay, so hi everyone. By the way, I hope things are going on as expected, and glad to see a lot of people still holding up after 1 hour. That means many are interested to sort of go through what has been taught. So, cool. If you have sort of questions, I've been answering most of them at the chat box. I think most of them, I would say. Yeah. So, if you have questions still, so please do drop in. And yeah, there are some questions which are just put across here. Yeah, so you could actually register at lms.sfslab.com. If you go there, there's an option called webinar. If you have registered over there under the webinars, yeah, we will add the course there, and also we will send an email with the recordings, right? So that would be the approach, how you would be able to receive the certificate. Sorry, not certificates, the recordings. All right, so for other people, eco mode and sport mode in EVs are restricted by discharge currents only. Yeah, so you could limit the requirements at the motor. So once you limit your requirements at the motor, so yeah, at the controller level, you could definitely limit that at the it doesn't even pull the higher currents from the battery pack. So it's like in a way to think, it's a vehicle architecture. If you see ethers, so they have like between your motor controller and the throttle, so you have a BCM, body control module. So like in a way, things are sort of architect architected to function in a way. So it totally depends upon the vehicle architecture, how the control is done. But in a general way, yes, when you have like sports mode and echo mode and stuff like that, you could send a signal to your BCM, and BCM would send a signal either to your depending upon the architecture, to a BMS or to motor controls and stuff like that. So it's more sensible to send it to motor controls because as a functionality of the controls of the motor is limited there itself. So you don't need to draw more current from the battery pack. So yeah, that's an answer for your question. Uh, you're working with OEMs, provide services to OEM simulation in MATLAB. To certain cases, yeah, we are helping out. Like OEMs are quite a bigger scale, so we don't directly sort of deal with OEs. So we could be tier one, tier two supplier connections, and we work with them. Okay, so which one better optimization method for battery optimization? The power of EV. Which one of better optimization method? Okay, Sakshi, would you mind to just put that question, sort of rearrange that question? So it would be great to sort of get it. Omkar, do you provide online courses on BMS? Yes, Omkar. So we have Omkar. So we have some of the programs dedicated to EV. So yeah, I could just share some link to you. These programs are available at this link, and this we have partnered with Formula Bharat too. There are programs starting on 28th. The batch size is quite small. It's limited like 10 to 12 people for a batch. So you could visit there. They are named as internships if you're a student, and they are named as a courses if you're a professional. So through that, we are teaching some of the content definitely, which can be taught is being taught over there. And yeah, you can surely visit. We have programs on level two, which is basically a way to start with, and then we have level three, where you'll be able to sort of gain very in-depth exposure to Kalman filter-based SOC estimations and stuff like that. So yeah, said that okay, right. I think that can be answered by Venu. Is safe, but simulating the trigger voltage in his peak at one, so we at zero, or how is it that? Okay, I think Amil, so that can be answered by Venu. Definitely, he's a model expert. So Sakshi, request you to provide some webinar related to battery and supercapacitor combination. Yeah, we will look forward definitely. That's a quite interesting area. I have a friend who have about 2 3 patents in that area, who worked on batteries and supercapacitor combinations. Sounds great. I'll ask him if so he can do it, but I'm not sure though. We require one resource develop simulation in MATLAB for one in EV project in OEM. Yeah, surely, Sunil. I will share you my email ID. I think we can definitely connect across. I'm just dropping you my email ID here. Uh, yeah, I have just dropped you my email address. Yeah, this is my contact. I think we can take ahead discussions. I'm sure we could surely help you out with either virtual or like a full time at your facility. Yeah, definitely we can take it ahead. Why not? We will be very glad to do that. So cool. So we have another question. In India, use 48, 72, 60. Why not go for a higher voltage? Okay, a very good question, Piyush. See, like the voltage architecture depends upon also like the current ratings you would like to handle. And also the other parameter is certain regulations. If you go for a higher voltage, obviously if you're going for 72 or going for higher voltage, so you need to ensure that the higher voltage safety systems, because that's a very critical system. If you go over 60, it's called as an high voltage. So it requires like a lot of high level protections, like in isolation monitoring systems and stuff like that. So one is, it is not easy to sort of manage a system, and like I would say is a safety perspective of it, and to ensure the functional safety perspective of it. And so I think as far as some of the players, if you see a scooter market, so it's more than sufficient if you're building a pretty a simple scooter without higher performances. Add to operate at 748, so your system is not a challenge in terms of safety. But yeah, definitely if you go for higher high performing systems, you will have to go for higher voltages. For sure, any of your Tata Nexon would have been there at lower voltages. It should be a higher voltage system. So it depends upon what is your load characteristics of the vehicle. So to maintain the load characteristics, what is your motor torque characteristics you have, and then if that's sufficient to handle the voltage, current, so it should be good. So, right. Hands-on experience in new technology decibels lab. Okay, Priyanshu, so we are not allowing anybody to come to office, and all of us are right now at work from home. So I don't think so it's something possible right now that we could do it. We will surely look forward for the future. All the courses at decibels are typically practical, so online courses. You could look forward for that. I think, yeah, very soon as things settle down, we may come back. Okay, all right, Venu, I think that's pretty much from my side, and all the questions here. Over to you back. Thank you.
Yep. So yeah, we'll start again. So now we are done with like the measure functionality, the production functionality. I will start ahead with estimation functionality of the BMS. So in estimation, what is the major important thing that we have to estimate is like state of charge. Okay. So what exactly mean by state of charge? We have discussed like it's nothing but the amount of capacity or the charge that is present at that point of time. Okay, showing that in like percentage level. So if you look at our like time t equal to 0, it might be at like SOC equal to 0%. And as time goes on, the SOC is increasing to 100%, which means the capacity in the cell is increasing from let's say like 0 to like 6 ampere, or like whatever the capacity of the cell it might be, 10 ampere or something like that. Okay. Only thing is like we are keeping some amount of charge into the cell, which is nothing but I into T. Okay. So for that, how we can estimate the state of charge at each and every second of time? So there are many ways we can estimate the state of charge. Okay, but how? But the thing is like accuracy and how difficult the estimation process is and all the stuff. Okay, mainly thing is like accuracy. So if you look at over here for that estimation of all these things, state of charge, the state of health, or equation the cells, we need to have like a measured current, voltages, and temperatures. Okay. So this we already have like the data. So now we'll go for like estimating the state of charge. Okay. Before that, we also discussed like why it is important to estimate the state of charge. Okay. So if you take like combustion vehicles, there we are having like a fuel gauge. It is showing like how much amount of fuel is left out in the tank, and based on that we can estimate like how far we can go. So similarly in the electric vehicles there has to be a parameter telling us that how much amount of energy or capacity that is present in the battery pack, so that based on that we can estimate our range. So the best example for this I can give you is like the Ather scooty which is in Bangalore. They're having like a strategy that like 1 minute charge equivalent to like 1 kilometer, something like that. I'm not 100% sure about the data, but yeah, they're having some strategy like that. So what happens is like if you know that strategy of charging for 1 minute means like charging like 1% or something like that. So that will give you like this much of range. So that based on that we can plan our things. Okay, so I want to go to office. So I can charge at home and I can reach office and I can keep it over there for charging. If you're not having that particular idea, then it will be like very hectic for us to maintain these electric vehicles and stuff. Because nowadays countries like India, it's very difficult to have like charge stations at each and every point where we go, because like, yeah, there are many issues with that. Okay, so that's a very important. So, and yeah, we discussed like electric vehicle range, and third important thing is like energy consumption. Okay, many people will be talking about like mileage. My vehicle will be giving this much of mileage. So in electric vehicle terms, it is like energy consumption, which is nothing but per kilometer of range, how much of energy it is consuming. Lesser the energy consumption, more is the efficient of the vehicle. Okay, so to estimate that, we need like a SOC. And next one is like, if you're talking in terms of like hybrid electric vehicles, there will be like different energy sources. There will be like a combustion energy source, there will be like battery, and there will be like a regeneration energy resource. So how we can manage all these things? Okay, how we can maintain the state of charge of the battery? That plays a very important role. So if you're not having proper estimation of stock, then maintaining all these three energy sources will become like a very hectic thing. So there we'll be having a two things. One is like a charge sustaining and charge depletion modes, which means like maintaining consistent state of charge, or like continuously varying the state of charge between the two limits. Maybe something like this. Let's say like this here is 60 and this is 30. So continuously varying the state of charge between this. So if you want to have this kind of control strategies, then estimation of SOC plays a very important role. And as we discussed, to make the work cell work in like a best operating regions, this is nothing but like a SOC window 90 to 10%. There also this plays a very important role. And to analyze the battery performance and reliability, lifetime of the battery, and the important thing is like cell parameters, R naught, which is the internal resistance of the cell, R1 and C1. These are like why I'm talking these electrical terms over here is there are some models, lithium-ion cell models, that were developed to understand the dynamic characteristic of the cell. Okay, if you are from like other background apart from the chemistry, then it will be very difficult for you to go into like a chemistry and understand like physics-based models and all the stuff. So for that reason, there are some models where they converted like chemistry-based models to like electrical term-based models, where anyone can understand those things. If you are good at like electrical and some simulation, then yeah, anyone can understand this. So there, those models are given name as like equivalent circuit models. Okay. So in those modeling, we'll need like these parameters R0, R1, and C1, and each parameter has like some what you call importance in terms of chemical. So this R0 represents like the resistance, internal resistance. I mean, like the flow of electrons will take place, right? So the resistance to flow of electrons. And R1 and the C1. This C1 is like we'll be having like double layer capacitance, or like double layer inside the cell. So each and every parameter is having like some importance in terms of chemical. So these parameters were all dependent on state of charge and temperature also. So that's the reason if you're having proper estimate of state of charge, then we can estimate proper R0, R1, C1. If we can estimate this, then we can, for any current profile, we'll get like lithium-ion behavior, something like this. If you want to get this behavior, then these parameters plays a very important role. Okay. When I'm showing like SOC model, I will show you like where I'm using these parameters and whether we are getting this behavior or not. Okay. And the cell balancing strategies are solely dependent on the cell SOC. For that, we have already discussed. So what are the available strategies for estimating the state of charge? So you can look at over here, like we are having like so many methodologies or categories. Okay. So, but out of all these things, I'll mainly discuss like three important strategies that we are following. One is like voltage-based methodology. So this is also called as like voltage lookup table-based methodology. And another one is like Coulomb counting-based methodology, or current integration methodology. Okay, both are same. In the adaptive systems, we are having like different types of BP neural network, RBF neural network, fuzzy neural network methodology, and Kalman filter. So today I will try to show you like a Kalman filter based methodology of estimation of state of charge. Okay. And the hybrid methods, which are a combination of like direct measurements and bookkeeping estimation, and our bookkeeping estimation with adaptive systems. The main aim is to like increase the accuracy of the estimation. Okay. So First, I'll discuss voltage-based strategy. So in this voltage-based strategy, what we are going to do is like we are going to develop like a lookup table, which is between voltage versus the state of charge. So we'll be having y-axis the voltage, and we'll be having like a state of charge on the x-axis, and we'll try to discharge the cell at lower C rates. So there is a reason why we are discharging at lower C rates also. So this lower C rates, it's up to you. Basically, they will tell like C by 20, that is mentioned in like data sheet, but it will be good to go around like C by 40 or C by 50. So the main aim of going very lower C rates is to decrease the dynamics within the cell. Okay. So in order to have like stable performance from the cell, then only we can get this kind of exact behavior. Otherwise, what will happen, like we'll be having fluctuations. Okay. So that's the reason we'll have like lower C rates. So then will correspond like let's say like at this point of time we'll be having like let's say we are having 10 amp hour cell. So when SOC equal to 100%, this is like 10 amp hour. So this corresponds like 100% SOC. So at each and every point of time we can measure the current and we can measure the time. If you multiply those two things, we'll get like capacity. So this capacity might be around like 8 amp hour, so it will be like 80%, something like that, and we'll come to like 10% and 0%. So here we'll try to compare these two things again. So here we'll be having some voltage. It's a 4.2 volts. So 4.2 corresponds to like 100%, and 2.8 corresponds to like 0%. Okay, so this lookup table will implement in the strategy or the algorithm. So whenever we are discharging the cell, so at each and every second of time, we'll be getting the voltage, or it depends upon the frequency of collection of the data. So if you are using like a low frequency, then we can get a lot of data, which means like a 1/10 or like a 1/100 milliseconds, something like that. So we can collect a lot of data and your estimation will be more accurate. Okay. So when you measure the voltage from this lookup table, we'll give the input as a voltage, measured voltage. So here we'll be having like a voltage versus a SOC table. So from this, we'll be getting the SOC as output. Okay. So this is something like a y equal to some mx plus some equation. We can't say this is that linear equation, but we have to use curve fitting tool to get this equation. Then only we'll get some equation over here, and we'll get like SOC. But do we think like this is the accurate method of estimation? No, there are like some problems in this also. Okay, so what are those problems? So the voltage that we are measuring will be highly affected by these parameters. One is like the amount of current that we are discharging or charging. Okay, because yeah, if you're going like if you're using like commercial vehicles, we will not use them for like abusing purpose. But if you go for like race car applications, we'll be suddenly going from like a -100 to like a plus 200 amps of current change, which means the cell dynamics will be totally changed from like a charging stage to like discharging stage. Okay, so in that situation, so the voltage graph will be totally affected, and SOC estimation will not be that accurate. So that's the one condition, and the temperature will affect the thing. So if the temperature increases, the reaction kinetics, electrokinetics, and the which means like the rate at the reaction taking place will increase. Okay, if it increases, then it is good. But increase of temperature is, I mean, like if the temperature increases too much, then the reaction kinetics will cross the safe zone and it will enter like unsafe zone where like unwanted gases will start generating and the cells will start like bulging. So these kind of things will happen and it will result in like short circuit. So if short circuit happens, the voltage and the measurements will be wrong and all this stuff, right? So that's where it is. And how we are operating the cells. So these are the things which will affect the voltage measurement. Apart from these things, we also have like some kind of noises, sensor noises, measurement noise, or like uh, process noise. So there are some things which we have to consider while measuring these things. So in this particular methodology, there are we are neglecting those things. Okay, so that's the reason we can't tell that as like a very accurate method of estimating the state of charge. So how we can make it more effective by including all these negative parameters that we discussed, like including the sensor noise, process noise, or like measurement noise, and also like creating a correction term according to the battery current. So if the battery is varying this much, so there has to be a term which will tell like, okay, the voltage has to be this much, like that. Okay, and by using a lookup table, not only with respect to state of charge, with respect to temperature also, so that we can consider all these 3 points. Okay, so this is the one way we can make it more accurate. So this is one of the algorithm. And next one is like a Coulomb counting strategy. So the name itself is telling that we are counting some coulombs. Coulomb is nothing but charge, I into T. So we are always counting the coulombs with respect to time, and we are telling that the cell is charged this much percentage or something like that. Okay, so the formula that is used for Coulomb counting strategy is this one: SOC at time t equal to SOC at time t minus 1 plus or minus IDT by 3600 into Q. Okay, so Q represents like nominal capacity of the cell. So here we need to have like a reference point, which means like initially when you charge the cell, it will reach like 100%. Okay, but after using it for a certain point of time, then it might end up somewhere at like 70% or 71%, something like that. Okay, so that will become very difficult for the BMS to predict that reference point and resetting it to this resetting this measurement to 71%. Okay, either it will work for like 100% or 0%. Okay, every time you have to reset the values. So that's the one of the problem with this thing, and no measurement can be perfect as per the analysis. Like there has to be some noises and all the stuff, and the electronic components that we're using for the sensing or like for analyzing data and all the stuff. Because if you look into the BMS, everything like electronic or electronic component. So for each and every component, there will be like some drift. So that is the one thing, and yeah, lack of reference point. So these reasons made like, yeah, of course, some of the people are using Coulomb counting strategy still in SOC estimation. Okay, but um, like the research is more on like towards like using more accurate strategies like EKF or like neural network methods, data-driven models, and all this stuff. Okay, so that's where we are coming up with like a Kalman filter strategy. So Kalman filter, I hope you might be knowing about the Kalman filters. So there are like based on like algorithm, and the main aim of this Kalman filters is like to estimate like unknown variables from the available data. So here the unknown variables is like state of charge and the terminal voltage. And the available data we are having is like current measurement, voltage measurement, and temperature measurement. By using these three things, we have to estimate the uh, SOC and VT, which is the terminal voltage. Okay. So why we are going with this Kalman filter strategy? So it to overcome the shortcomings of those methodologies, or voltage-based methodology or like current integration methodology. Apart from that, we can implement the cell model in this Kalman filter strategy, which means in these two strategies, Coulomb counting and voltage-based, there is no model which is talking about like how the cell is behaving. But here we can implement like the cell model itself, lithium-ion equivalent circuit model. Okay. So this makes like this strategy more accurate for estimate of state of charge. And apart from that, it is relatively simple form. Until unless you know the Kalman filter, it will be very difficult. If you know the Kalman filters, then it is like a really simple and requires small computational power, and it's like a high precision. Okay. And apart from this, I have told like sensor noise, measurement noise, or like error covariances. So all these things can be input into this model. Okay. So that's why this is like one of the advanced or like more accurate way of estimating the state of charge. So how to develop the Kalman filter algorithm? In Kalman filters, we are having like two steps. One is like a prediction step and update step. Okay, so this prediction step is also called as like a propagation step, and the update step is called as like correction step, which means like initially we'll predict some value. So let's say like initially we'll give some 100 as our state of charge. In the next step, it will predict some state of charge as like 99%. So this 99% will be sent to like update step. In the update step, there will be like Kalman gains and some error covariance that will be added to this particular thing. Okay, so then they'll update this value to like maybe 99.99% or like 98 percentage, depending upon the real Kalman gain it is taking and all the stuff. Okay, Kalman gain is something like controller. So yeah, it will control this output. Okay. So if you look at over here, this is the process that the Kalman gain will exactly follow. So for that, first thing you have to do is like you have to use some inputs, initial inputs. So that is nothing but initial estimate. So we always know like 100% is our initial estimate. So we'll give that 100%. And error covariance values, these are nothing but like noise value or like process noise, measurement noise, and error covariance values, these things. Okay. So covariance is like a very large topic, huge topic. Okay. But that is like very, really interesting to learn covariances, how to calculate the covariances or like average values and stuff. Okay. So we'll give those values as inputs. And in the first step, before doing all these things, we have to develop some state equations because Kalman filters will mainly use state equations. So state equations are nothing but like the equations that represent how the system is working or how the system is behaving. Okay, so if you know about like a state space models, then you might be knowing about these state equations, how to develop this, how to write these state equations. So after getting the state equations, we have to convert them to like a discrete form. Always the Kalman filter asks for like a discrete state equations. Okay, there is again like a process how we can discretize the continuous time domain equations to like a discretized time domain equations. Okay, so after converting them, then we have to form like a state space matrices, which are called as like a state transition matrix or like input coefficient matrix or output coefficient matrix, like that. And then we have to start with this particular process. So if you look at over here, AD and BD are like the state transition matrix. So AD is the state transition matrix, BD is the input coefficient matrix, and this is the output we are expecting. Okay, xk by k is like the previous or like initial state. Okay, and uk is the input. So here the input is nothing but current. So based on that, it will calculate the state of charge, and that will be given as output over here. Yk plus 1 equal to cd is like again output coefficient matrix, and d is like output coefficient for input. Okay, so then based on that, it will calculate like error covariance, and then we'll move to like a Kalman gain. So if you look at the, yeah, so this is the Kalman gain we are calculating. After calculation of the Kalman gain, we are going to give some correction to the estimated value. So here we are estimating some value, right? So here we are estimating some value. So we have to give some correction to that, which means like it's something like PID controller, just for time being assuming like that. So we are giving some reference value, and we are sending it to the system, and from that we are getting some output, and output is given back to the here. Sorry, here there will be like a PID also. This is the controller. So plus minus. So this PID will tune this signal such that we'll reach the output as equivalent to a reference signal, right? So like that here, the Kalman gain will tune the output to reach the reference value. Okay. So here yk plus 1 minus yk minus 1, which is like reference minus output we are getting times Kalman gain. So that's how this Kalman gain works. And if this Kalman gain is like one, it will be always between like 1 and 0. There is a reason why it is between 1 and 0. And there are also like reasons like what happens if it is 0 and what happens if it is 1. If it is 0, if it is 0, then it is like totally depend on like the process that we are going. If it is like 1, then it depends on like the system. Okay, which means like whether it is depending on the system or whether it is depending wholly on like the measurements. So like that we have to do analyzation and all the stuff. Yeah, finally it will calculate the error covariance value. Okay, so after calculating this, again this will come over here. So it will be like a continuous loop. Okay, so what I would suggest you is like take this step by step. Like first step, this one, try keeping k equal to 0 in this equation. Okay, so do step by step, right? All the, like we are having 6 steps, right? So first step, second step, third step, 4, 5, 6, like this, with k equal to 0. Then write the same equations with k equal to 1, and write with k equal to 2. At least do for 2 or 3 iterations. Then you'll clearly understand how this is exactly working. Okay, so whatever the output coming over here will be used as input in this k equal to 1 iteration. And whatever the output coming over here will be used as input in this k equal to 2 iteration. But I would strongly suggest you like, because I can't explain all those things over here, just keep k values and try to analyze that process. You'll clearly understand like how it works. So yeah, that is the Kalman filter algorithm. And this is the model uh, which I have developed for estimating the state of charge using the extended Kalman filter. So as I told you here, we need like a data. One is like a current data and the voltage data. So here I'm giving, this is the input current profile, and this is the voltage that is measured. Okay. So we have to predict state of charge. How we can predict the state of charge? We can use some methodology to predict the state of charge. So I am using Coulomb counting based methodology to predict the state of charge, but in discrete domain, not in continuous time domain. In discrete domain, I'm estimating the state of charge, and then I'm sending this estimated value to the Kalman filter. Okay, but here if you look at over here, I'm giving the output of Kalman filter SOC update. That is nothing but output. This output is again given as input to this RC circuit parameters and the Thevenin model. So these two were called as like a cell model, lithium ion cell model. Okay. So whatever the SOC we are giving over here, we'll be calculating in this block RC parameters, which is nothing but R0, R1, C1 and stuff. And these values will be given over here. And if you know these values, we can calculate like our circuit will be something like this. Okay, so this is R0 and this is like R1 and this C1. So this is like open circuit voltage and this is like the terminal voltage, this point. So we want terminal voltage. So, and these are like dependent on state of charge. We can calculate the voltage drop across R0 and voltage drop across RC circuit. And if we subtract those two from the open circuit voltage, we'll get the terminal voltage. So that's what we are doing it over here. And we are getting like a cell parameters, which are nothing but like voltage drop across RC circuit and the terminal voltage. And those two things I'm sending it to the Kalman filter over here. And in the Kalman filter, I'll do these 6 steps. Okay, so then it will goes in the loop every time, and we'll get like each and every second we'll get the update over here. Okay, I'll try to show this model in the MATLAB. Okay, but then we'll be we'll be getting some idea about this. So yeah, basically this is the code that I have written for estimating the state of charge. So first I told you, right, we have to understand the system or like the battery model. So here I'm using like a 2RC Thevenin battery model. So for that battery model, we have to write the state equations. So this is how the state equations will be. State equation 1 and state equation 2. And then I am writing the state equation 3. State equations are always depending upon like what are the outputs you are expecting. So those things has to be always your state variables. So here I am expecting like a voltage across the RC circuits and the state of charge as the outputs. So that's why I have taken these 3 things as variables. And the output equation is like I'm expecting terminal voltage as output. So I am taking this equation. And after that, I'm converting them into like state space equations. So how to convert the state space equations? Like we have to select the state variables, input variable and output variable. And then we have to write them in state space equations. And then we have to convert them into like equations. Sorry, not equation, matrix. So this is like a state transition matrix, input quotient matrix, and C and D matrices. Then I'll be employing like this Kalman filter procedure, all the 6 steps. Okay, so yeah, this is the thing which I have developed. But yeah, I'll try to run this model and I'll show you some results. So this is the how the voltage across RC circuit is behaving. This graph, okay, it is varying between like minus to like 0.04. So this is how much the voltage variation is happening across the RC circuit. And as I told you, like I am using two RC circuits, so we have to consider two voltage across RC circuits, right? So these are again like a voltage across the RC circuit one. So the validation point is like for a lithium ion cell, the voltage terminal voltage graph has to be something like this. So if you look at earlier, it is exactly behaving like this, but with some fluctuations because it depends upon like noise signals and everything. But yeah, in real case scenario also will be getting like this. After that, this is some error, and these are like state of charge values. I'll show you like exact state of charge graph. Yeah. So here, what I'm doing is I'm discharging the cell at like 1C rate, which means if you discharge at 1C rate, it has to come for like 1 hour of time, and the SOC has to come from 100% to 0%. So that's my validation. So I can go with like dynamic profiles and validate my profile. But the thing is like we can't validate ourselves. Like if it is dynamic and current is continuously changing, then we can't validate ourselves like whether the model is working good or not. So for that, I went for like a constant current discharge test. Okay, so now here I'm discharging for like 1C rate. So if you look at this is like 100% SOC, and it slightly coming down to like a 0% within like a 3600 seconds. Okay, which means both the time and the SOC both were validated. Okay, which means the model is working good. So with this only, we should not stop it. We have to do it for like a 2C or 3C or sometimes 10C rate. So that what happens is like if you are operating a 10C rate, so the SOC has to come to from 100% to 0% within the time of like 60 minutes by 10, which is like 6 minutes. Okay, which is like 360 seconds. Okay, so yeah, that's how we can validate the things. But yeah, validated those things, and it's working perfectly good. So this is the Simulink model which I have developed. The previous graphs are from like MATLAB coding, and this is like a Simulink based. So what I can do is like I convert all these things into like a C coding, and then I can dump into like a controller or like BMS that I'm going to develop. Okay, that option we are having over here. We can convert all these things into C coding. So this is the current profile I'm giving over here. Basically nothing. I have collected the data from the test, and I'm giving it over here. If you are not having the test data, what you can do is like you can generate your own current profile. So signal generator, yeah, we'll be having some option the Simulink, which is called as the signal generator. So you can generate the signals like this, and you can check your current profile. So as I told you, like these are like RC equations. So for this, in order to get these equations, we have to do some kind of test, which is called as like a hybrid pulse power characterization test, or like impedance spectroscopy test, electrochemical impedance spectroscopy test. So when you do those tests, we'll get like the resistance that the cell is having, and the resistance behavior and all this stuff. So based on that, for each and SOC level, we'll try to get the data, and we'll try to form a lookup table. And based on that lookup table, we'll try to estimate like how the internal resistance of the cell is varying with respect to state of charge. And those equations were kept in these blocks. Okay. So these things, what we'll do is like initially here I kept like this is like starting point. I kept it as like 100% initial condition. So at SOC equal to 100%, it will calculate R0, R1, C1 and the data, and it will send to the cell model. So here I'll be calculating like the voltage across the RC circuit and the terminal voltage. So that I'll be using back in my EKF Kalman filter. Okay. And another thing is like SOC prediction. We have to predict the SOC values, right? So for that, as I told you, like I am using a Coulomb counting based methodology, but with like a discretization. So this is like the discretization form of SOC, and I'm giving that as input to the Kalman filter. So now if I go into like Kalman filter, this is like a MATLAB function I'm using. I can write all the code which is needed for estimating the things with the necessary inputs. Okay, Q and P values, which are nothing but like the sound values, noise values. Sorry. So those things, and UL observed is the tested data, and these are like predicted data. SOC predict, UL predict, time constant, everything we have to give as inputs, And in this MATLAB function, I have written the code for estimating all those things. Okay. So now we are getting SOC update as the output. So if I now run this particular Simulink model, you can observe these two things. This thing also, the SOC is continuously varying. So it has started from 100 and ended it over like 0. And this also is started from 100 and ended at 0%, which means like it's exactly coming for 1 hour of time and it's reaching like 0% SOC. Okay, which means the model is working perfectly good. And I have validated for like dynamic profiles also. So yeah, this is the SOC estimation using the Kalman filter. In a similar way, we can develop for like SOH. There is no change except like some state equations. Okay, the Kalman filter procedure, everything will be same. So I'm not going to like again show this model for SOH. So here we'll be giving the, instead of current profile, we'll give like a capacity profile, because there are two ways of estimating the state of health. Okay, I'll discuss that theory, but yeah, I'll give the capacity over here and I'll try to calculate the remaining things. Okay, so there is no change in that, just like small modifications we have to do in SOH. So this is like SOC model estimation. So now I'll move to like a state of health. State of health is nothing but like the amount of capacity that has been lost in this period of time, some period of time, like after some cycles of time. Okay, so that's why here we have written like SOH equal to Q actual by Q nominal. So yeah, in vehicular applications, we'll consider like sorry, yeah, in vehicular applications, we'll consider like 80% SOH as the limit, so that after when we reach like 80%, we have to go for like secondary usage of batteries. Okay, so as I told you, like, there are two ways of estimating the state of health. One is like capacity based, and another one is like resistance based. So which means like as time goes on, the resistance and the cell will be goes on increasing. So if we can find out like the resistance for each and every cycle, then we can develop the model and we can estimate like how the state of health is varying. Okay, so but what are the reasons for state of health? The main reason is like degradation mechanisms. So if you look at over here, these are all the reasons for state of health. Copper current in cell, we know, right, what are the different components we'll be having. So because of all those components, there are like many ways why the resistance will develop in the cell, or like why the capacity will be lost in the cell. Okay, so in order to understand all these parameters, I got like some nice tabular format over here, so that will give like a clear cut idea of what are the reasons, or like what is the cause of degradation mechanism, and how it is going to degrade, and what is the final effect. Okay, so for example, like we'll consider like we are storing the cell at like low temperature. Okay, so if you are storing the cell at low temperature, what are the things that might happen is, so this might lead to like lithium plating or dendrite formation. So because of this degradation mechanism, what is the degradation mode? So it can be like a loss of lithium inventory. Okay, if loss of lithium happens, it means like we are losing the active material. If we are losing the active material, then the capacity for sure it will decrease. And the next one is happening is like loss of active anode material. Both are nothing but like losing active materials. So here anode means like graphite. So if you lose graphite, or if you lose like lithium, both will lead to like a loss of capacity. So that's the reason loss of lithium inventory happens. This leads to like a capacity fade, and loss of active anode material, which leads to like a capacity fade. So the capacity fade is nothing but lose of capacity or over a period of time because of these degradation reasons. So that's the reason this leads to like a state of health, a decrement in the state of health after 1,000 cycles, or like something like that. So yeah, if you can find out like the resistance behavior, we can clearly implement that in the Kalman filters, and we can estimate like state of health. So the next important functionality is like cell balancing. So the main aim of this cell balancing is like to balance the cells. in terms of voltage or like in terms of SOC, state of charge. Okay, as I told you, like there might be one cell which is very weak. Sorry. So yeah, let's say like this is one cell and this is another cell. This is the weak cell, which means there is some problem with this, and this is a strong cell. Okay, so what might happen with this? If these two cells are connected in series. Okay, so when we are charging the cells, so this cell will reach 100 percentage within very less period of time, because this is a very weak, and because of that reason it will reach 100% very short period of time, but this will take too much of time. So when these cells are connected in series, we'll be measuring the cell voltage, right? So this will give like a 4.2 volts, but this will give like a somewhere around 3 volts. Okay, so then the BMS will start try to balance these two things. How it can balance? Okay, there are two ways of balancing these two things. One is like dissipative balancing, or second one is like non-dissipative balancing. So other names for these two things were like passive balancing and active balancing. So the reason for this passive and active balancing is like the components that we are using in the balancing. Okay, so here we mostly will be using like components such as like transistors, switching circuits, or resistors, something like that. Okay, so why we are like in passive, we are also using like some active components such as like transistors and switching circuits. They are like active components, right? So when you are using active components and giving the name as passive balancing, it gives some kind of confusion. That is the reason like most people would say like dissipative and non-dissipative thing. Okay, so what exactly happens in dissipative uh, or like passive balancing is, so whatever the weak cell is there, will try to drain the charge from that particular cell, because it is reaching the higher state of charge within a less period of time. So we'll drain the charge from the cell as like a waste in terms of like heat energy or something like that. Okay, that's what we are doing in the passive balancing. But whereas in active balancing, what we'll do is like we'll try to move the charge from the weak cell to the other cells or to the auxiliary load circuit, so that we can conserve some amount of energy. Okay, otherwise what's happening is like we are wasting the energy, so that's not the good option. So if you go with like active balancing, we can move the charge from one cell to a strong cell, or like we can store that in like a auxiliary battery, where we can use that for like auxiliary applications, or we can use them for like immediate useful purpose if you need like some energy at that particular point of time for some other electronic components. So at that point of time we can use this energy from that weak cell. So yeah, and these are some of the algorithms which I found very interesting from the Fox BMS website, and like I put over here. These are like really interesting. One is like voltage-based balancing and SOC-based balancing. So first thing is like we have to switch on the BMS and we have to initialize like the balancing circuitry. So then the BMS will go for like checking whether the cells are balanced or not. If they are not balanced, then it will go for balancing. And for each and every iteration which are mentioned over here, it will try to calculate the voltage and it will check with the other cells. If it is okay, then it will go for, I mean, like, it will go for checking, balancing. If it is okay, then it will stop the balancing. Otherwise, no, it will come for limit. So like this, it will goes on loop. And similarly for like SOC also. Here, instead of considering like voltage, we'll be considering like state of charge. So here I mentioned like the process, how exactly the cell balancing will happen. So what we'll do is like we'll charge the battery pack, or like we'll discharge the battery pack, whatever it might be, but we'll keep the battery pack for some period of time at rest condition, so that if there is any fluctuations in the voltage, because lithium ion cells will be having some polarization or like fluctuation. So if we charge the cell like this, so after some period of time, it will end up something like this, which means there is some voltage drop. Okay, when you do testing, we can observe this kind of behaviors. So in order to make the cell to come to the stable state, we'll keep the battery pack for like some period for rest time. Then we'll try to measure the SOC state of charge values by using the voltage lookup table method, or like whatever the methodology you're using. Okay, then from the state of charge, we can be calculating like a depth of discharge, So depth of discharge is nothing but like 1 minus SOC. This is like they both are like vice versa. So after calculating the depth of discharge, we'll get to know which cell is has been like a discharge very fast. Only the weak cells will discharge very fast. So that cell will be taking as like a reference cell, and then from other cells we'll try to calculate like the charge difference from with respect to the reference cell or the weak cell. Okay, so the charge difference will be calculated as like depth of discharge of reference cell minus depth of discharge of considered cell. Let's say like our depth of discharge of reference cell is like 20 percentage, and the considered cell is like 60 percentage. So the difference is like 40. So now we have to try to, this 40 percentage will be equivalent to some capacity. Okay, so then we'll try to balance this charging. So how we can balance is, as I told you, like there will be some passive elements as well as like active elements like resistors, transistors, and all this stuff. So if you know like balancing resistance, okay, and if you know like capacity, we can convert this capacity to the current. Okay, so we can measure like by using this current equal to cell voltage divided by balancing resistance. Okay, cell voltage we can measure like yeah, by sensing the voltage values. So then after getting the current, if you multiply again with the time, it will become like the capacity. So it's nothing but charge. We'll put that charge into the selected cell. So this is like algorithm which we'll be using for balancing the cells. Okay. I found it really interesting. This you can go through them if you're really interested in the cell balancing part. So yeah, with this we are done with like BMS algorithms and stuff. Okay, but each and every functionality I spoke about like lithium ion cell model, right? And I also told you like equivalent circuit model of lithium ion. So this is how exactly it will be looking like. This is called as like a Thevenin model exactly. So all the physics-based models are converted into equivalent circuit modeling. In equivalent circuit modeling, we are having like four different types. One is ring model, Thevenin model, dual polarization model, or neural network model. So we are having like four different types. So one of them is like this one, which is the Thevenin model. I found it like a more accurate model for estimating the parameters. So here every parameter, whatever you are seeing over here, open circuit voltage, capacitance, R1, R0, everything is a function of state of charge and temperature. Okay, but how we can find this data? So we can find this data by conducting a test called as like HPPC test, as I told you before, or like a EIS test, electrochemical impedance spectroscopy test. If we do this test, let's say like this is the HPPC test. The graph which I'm showing over is for like pulse characterization test. I'll give some pulse here, pulse current. Let's say like this delta is the current. So for this pulse current, we'll get like voltage behavior, something like this. Okay. So initially when there is no current discharge, I mean like current equal to 0, there is no voltage variation. But suddenly when the current drops, so the voltage also suddenly drops. So this sudden drop in voltage corresponds to like a ohmic resistance. And after that, we are having like some variation, I mean like delayed response or like some curve behavior of resistance. So this is called as like RCT, charge transfer resistance, which means like when the charge is, we'll be having like electrode, which will be inserted in the electrolyte, right? So the charge will be transferring from electrode to electrolyte. So there will be some resistance between those things. So that one, and this is like a polarization resistance. So we'll be estimating for each and SOC level. So we'll do this test at like 100% SOC, 90 with a step of like 10 up to 0%. And we'll try to calculate like R0, R1, C1 values. Okay, and we'll try to form the equations. And another thing is like OCB curve. We need OCB also. How we can get that? So we have to do test called as like a static capacity test or like a constant charge test or discharge test with lower C rates of C by 20 or C by 30. So when we do these things, you'll get like a stable plot of OCV with respect to the state of charge and also with respect to temperature. And yeah, the third one is like estimation of capacity. This can be done using like a static capacity test, which is very similar to this one. So these are the different types of tests that you have to do, and then you have to develop the model. And from that model, you can estimate all the behaviors, like how the cell is behaving and all this stuff. Okay. So yeah, with this, I think I have completed all the stuff. And yeah, these are some of the references which might be useful for you. And finally, thank you everyone. Thank you so much.
Thanks a lot, Bruno, for making all quite interactive. And thanks a lot for the detailed discussions. I have answered almost all the questions that I could possibly touch base. Yeah, I think if there is something that you want to see through, and kindly just look through the chat box. I have almost answered all the questions. Just yeah, somebody who felt the questions are not unanswered, like not answered. So like, please do drop them back again. We should be able to take them up. So yeah, in the meantime, you guys have any questions, you could drop it in. By the way, I would like to just share a small details across to you regarding the programs we have in the upcoming line. If you're interested to sort of learn about EVs, so if you're a very beginner, you're starting all from scratch, so we have some of these programs. So this is a program which is about $999, which is starting on the 4th of January. The intention of this program is to like provide a very solid foundation, not just finding some things in internet and assembling them into a PPT, but it is more in depth of a discussions about all the components and what kind of architectures are there and stuff like that. So if you're interested to begin with, you could start with the program which is Electric Vehicle Technology Certification course. And if you want to perform something further as a learning, so you could start with lithium-ion cell and BMS algorithms, which is a pretty structured course taken by a lot of people who are willing to start something in the areas of battery management system. We have defined the content where all the courses are 100% practical, where you will have the laptop on the other side, where you will build the model along with the trainer. And if you have any queries or questions, you sort of ask them right away during the live sessions. It's like a same sort of a session which is happening now, but the size of the participants will be quite limited to like 10 or 12 people, so that everybody's questions can be answered and addressed right away then and there. So once you're sort of graduating with a level 2 lithium-ion cell and BMS algorithm MBD, you could go for the SOC, which is based on an EKF. So we have a detailed modeling approach, which will be taught by Venu on the program. So you could look for it. Right now, we don't have the dates for this. It's planned for the next January. So we could share across the details. If somebody is interested, you could just drop us an email to contact@decibelslab or admin@decibelslab, or even suraj@decibelslab. So somebody would like to explore something in the areas of testing, specifically like how the cell is tested, what are test equipments used, what is type of tests are conducted, and the data which we get from the testing. So if you want to analyze all of that, then cell testing is the fantastic course for you. So I would say somebody want to begin with in the areas of areas of cell and explore opportunities in testing engineer or a cell level or a pack level, or you can also understand the cell and BMS algorithms. Cell testing becomes a very, very primary requirement, because we need to understand how the cell behaves, and without understanding how the cell behaves, there is nothing much we could do on the cell and BMS modeling as sort of a thing. So it would be a good foundation skill to start with, to understand the cell characteristics. It's a detailed course which helps you to gain a very good in-depth insights on the cell and its behavior. Then to start with the level 2 or a 4-week internship as formative for students and professionals, and then the EKF based things. And we are also coming up with SOH estimations, and also cell pack level BMS with cell balancing. That will be an addition in the future. We will share the details across to you over the emails if you're registered for the program. So most of the programs are starting on 28th of December. If you're looking forward to take part in any of these programs, yes, sure. You could plan ahead your calendar, and if you have any queries, you can always reach us to contact@decibelslab, or one of our member will support you on the activities. Cool. So that's pretty much from my side for the queries. Uh, let's go back and ask if there is any questions there in the chat box. Cool. Looks like there are a few questions. Okay. All right. Guys, usually we don't share the presentations because they were misused by a lot of people in the past. We could share the recordings. So for the needful, kindly make use of that. Great. So thanks a lot, Prashant, for the great interactions, and we will surely look forward to see through the documents. Great. Okay. Then great. So that's pretty much then. Cool. Guys, if you would like to receive any notifications, like go to Decibels Lab website, you can just create your account in Decibels Lab. We could just communicate to you, or you could just follow us in LinkedIn or Instagram. All you have to do is just go down here, go to webinars, and then just because I already brought this and just my resume, just click on enroll now, and you can enroll for this link. And if you enroll for this link, so you will receive notification of all the webinars. We have done a lot of webinars in various topics in the past. I think most of them are available in YouTube too. So yeah, if you're interested for getting notifications on quality webinars, so you should ensure and sign up to this webinar series from Decibels, so you will receive the notifications from Decibels. Okay. Okay. So great. Pleasure and thank you. It was great interacting with all of you. We're glad it will help you out. So in the future, and we look forward to being in touch with you. So keep working. I think industry requires good engineers, and I think as in curriculums available in academics, we still don't have enough quality content. I think anywhere, by the way. So at academics, so I think the courses like this could definitely help you, and they have helped a lot of engineers to start their career. I'm sure it could help you too. So pleasure, and thanks for being the amazing participants, and thanks a lot Venu, for making the sessions very interactive and sharing all the depth of information. So thanks a lot everybody who have shared your queries, and thanks a lot people who have also shared certain inputs during my chats, and we'll look forward to keep improvising, and we'll look forward to learn and engage. If you have any requirements, you can always drop an email to suraj@decibelslab.com. I'll just drop my email ID here. It's suraj@decibelslab.com. Yeah, that's my email ID. So you could drop us an email if you have any queries regarding the things. Then be in touch and keep learning. Keep safe for yourself. We'll look forward to see you in the upcoming webinars, and all the best for future endeavors. Thank you. Thank you, everyone. And thank you, Lord Venu. Good night, everyone. See you soon. Bye-bye. Take care.
Thank you.
Thank you, everyone. Good night.